पूचंग पर्यात छंद नमो सर्वमाने समस्ति निधाने नमो देव देवे अपेक्षी अपेवे अर्थात salutation to thee, O universally honored Lord. Salutation to thee, O the treasure Lord. Salutation to thee, O greatest Lord. Salutation to thee, O garbless Lord. Unit 2 Solutions Part 1 Raoult's Law. Dear students, let us understand the concept of vapor pressure with the help of this animation. Here there is a closed beaker in which we are adding some solvent. It may be water. Water is added into this beaker. Now what happened to the water? Practically the molecule of surface heated by the bulk molecule, and it may move to the gaseous state. Okay, its energy becomes high, it goes to the gaseous state as we are seeing, and this process is known as evaporation. The molecules of the in the vapor state may come into liquid state and join the solvent, and this process is known as condensation. If the rate of condensation become equal to the rate of evaporation, then equilibrium is attained. At equilibrium, the pressure exerted by the vapors above the liquid surface is called vapor pressure, and vapor pressure denoted by P naught 1. Now what will happen if we add a non-volatile solute to this solvent as shown by some brown dots, and as we are seeing that non-volatile solute, it may be NaCl, also occupies some surface area. Due to this, the number of volatile solvent molecule escaping becomes less. Lesser number of solvent molecule will go to the gaseous state, and the molecules coming from gaseous state to liquid state will also be lesser, and hence at equilibrium the pressure of vapors will also be lesser. Vapor pressure of solvent in a solution is represented by P1. Now lowering in vapor pressure will be P1 naught minus P1. And now what is vapor pressure? The pressure exerted by the vapors above the liquid surface in equilibrium with the liquid is called vapor pressure, as you see in the red. And now vapor pressure of a liquid decreases when non-volatile solute is added to it in blue. In green now, this is due to the fact that reason is given that the non-volatile solute particle also occupies some surface area and number of solvent particles escaping becomes less, hence vapor pressure decreases. And P1 naught, P naught 1 the vapor pressure of pure solvent, P1 vapor pressure of solvent in solution, then lowering will be P naught 1 minus P1, as we already seen with the help of animation and with the help of this theory. And now we move to the next topic, Raoult law. Raoult gave a quantitative relationship between partial pressures P1, P2 and mole fraction X1, X2 of two components present in solution. Suppose I have component 1 and P naught 1 be the vapor pressure of component 1 in pure state, and I have component 2 and P naught 2 be the vapor pressure of component 2 in pure state. I am mixing these two components and getting the solution. In solution, P1 the partial vapor pressure of component in solution, P2 partial vapor pressure of component 2 in solution, X1 mole fraction of component 1, X2 the mole fraction of component 2. The word partial is used, partial vapor pressure, for any component in solution. The reason is that we can't exactly measure the vapor pressure of component in solution. Exactly it is not possible. Therefore the term partial vapor pressure is used here. And then according to Raoults law, what is telling us for a solution of volatile liquid in blue, the partial vapor pressure of each component in solution is directly proportional to its mole fraction. Let's see mathematically. For component 1, P1 will be directly proportional to x1, and to eliminate this proportionality we introduce a constant P01. P1 will be equal to P01 x1 for component 1, and similarly for component 2 it will be P2 will be equal to P02 x2. And now graphical behavior of graphical behavior of Raoults law. According to Dalton's law of partial pressure, P total will be P1 plus P2, and substituting the value of P1 and P2 in equation 3, we get the equation number 4. And rearranging this, we get equation 5. And in equation 5, which is of the type y is equal to mx plus c, which makes us clear that the plot of vapor pressure P will be a straight line against mole fraction. And following conclusion can be drawn from equation 5. Total vapor pressure over the solution can be related to the mole fraction of any one component. Number 2, total vapor pressure over the solution varies linearly with the mole fraction of component 2. A plot of P1 or P2 versus the mole fraction x1 and x2 for a solution gives a linear plot as shown in figure. Let us see. And x-axis is mole fraction, and y-axis we are showing the vapor pressure. Graph 1 for P1, now for P2, and for solution P total. And graph 1, graph 2, graph 3. These are the graphs for Raoults law. And from x1 decreases on moving left to right, and mole fraction become the x1 becomes 0 at right, and x2 will become 1. In the same way, uh, at the top of x1 when 1, and then P highest pressure will be pressure of the pure solvent, pure component, that will be P naught 1. This is the graphical behavior from Raoults law. And we should know in the what will happen in the vapor state. The composition of vapor phase in equilibrium with the solution is determined by the partial pressure of the component. Let y1 the mole fraction of component 1 in vapor phase, y2 the mole fraction of component 2 in vapor phase. Then using the Dalton law of partial pressure, P1 will be equal to y1 P total, and P2 will be equal to y2 P total. In general, we can say Pi will be equal to yi multiplied by P total. And note to Raoults law as a special case of Henry law. We know the Raoults law Pi equal to xi P naught I, or we make say P1 equal to x1 P naught 1. And Henry law is P is equal to khx. If this P naught 1 become equal to kh, then Raoults law becomes the special case of Henry's law. At last, some homework has to be done based on Raoults law. We have three questions. State Raoults law, show that Raoults law is a special case of Henry law, derive graphical behavior of Raoults law, and one numerical problem is given here. And some important knowledge note: although Raoults law is valid for dilute, that is ideal solutions, keep in mind that it is valid for ideal solutions or dilute solution. It's applicable to concentrated non-ideal solutions, does not lead to variation of the order of magnitude of the calculated vapor pressure. Thank you for attending the lecture. Have a nice day. Be safe, be at home, be safe.